this one. All right, so let's talk through 2.1, number 7. So in problem 5, we had some stuff. Okay, good. And then they're saying this is a singular case. So I think the question was, what does this word singular mean? Is that more or less right?
Yeah, just what's meant by singular case.
Yeah, so what they mean by this singular case is they mean that the matrix 1, 1, 2, 1, 2, 3, 1, 1, 2 has linearly dependent columns. And essentially, the reason that you might care about having linearly dependent columns is that that means that this matrix, which I guess I'm going to call A for reasons, this means that A is not invertible. As a function. Does that thought process make sense?
Yeah.
I forget what dependence means, but I can just look that up in the book.
What?
I forget what the linear dependence means, but
okay. So linear dependence means that some linear combination of those three vectors will give you the zero vector without having all zero coefficients.
Okay.
So in this case, I can pretty well tell that the first column and the third column are copies of each other. Right. So I'm pretty confident that if I take A and multiply it by the vector 1, 0, -1, I'm going to get the vector, that first column vector, plus the 0 vector, plus, oops, not plus. No. Oh, great. My tablet has changed modes for some reason. Good. Perfect. So I'm going to have minus, right? Because this -1 is going to be applied to that third column.
Yeah.
So I'm going to have minus the vector 1, 1, 2. And this is going to result in the 0 vector, right? Now, another thing I know is that if I take A times the 0 vector, I'm going to get the 0 vector plus the 0 vector plus the 0 vector, right?
Mm-hmm.
Which is going to give me, huge surprise, still the 0 vector. You guys with me on that? Okay, so what's going on here is these are two vectors that are getting mapped to the same place, right? So in a kind of function picture, I have my matrix A that takes this space over here to this space over here. And what I found is that there's two values over here that get mapped to the same point over here. So that's the 0 vector over there. Right? One of these is the 0 vector, and the other one is that vector 1, 0, -1. You guys with me on that? So normally the inverse function would go this way, right? If it existed.
Mm-hmm.
It would kind of undo those green arrows. Well, the problem is that that thing's not a function anymore because the 0 vector would have to go to both these things, and that means that this thing doesn't exist. Does that follow?
Okay.
Anybody confused by that? I realize it may have been a while since we've drawn this picture.
So singular just means it only goes one way?
Yeah, you could think about a singular matrix as one where the inverse function doesn't exist.
Okay.
Is it safe to assume anything with the 0 vector is a singular case?
Anything with the 0 vector.
So like that maps to the zero vector, because the zero vector could, I guess, in theory, map to any or map back to any matrices.
So be careful, because all matrices are gonna map the zero vector to the zero vector. Does that make sense?
Okay, yeah.
It's not that something maps to zero, it's that something that's not zero maps to zero that causes
Got
the
it.
problem.
Okay.
Does that make sense? Don't worry, this is a concept that we're going to keep coming back to and touching on throughout the first half of the course at least. So believe me, you'll get used to me at least saying this. I'm hoping that you're going to internalize it and know that this is the case after a bit. Is that cool?
So
Okay.
because it has something that is the non-zero vector that turns into the zero vector, that makes it dependent, right?
That makes it what?
Dependent.
I just didn't hear you.
Oh, dependent, like linearly dependent.
Yeah, that means the columns are linearly dependent.
Okay. And then
Linear dependence really is the thing that's going on here. So I'm a little bit hesitant to kind of put the arrows in that sentence. Those are really the same thing, right? If the columns are linearly dependent, then the matrix maps a non-zero vector to the zero vector, and either of those things are the same as the matrix not being invertible.
okay. So when it's okay.
You guys good with that? Okay. So singular really just, you could think about it as meaning it has linearly dependent columns. That is so closely related to it's not invertible as to be the exact same statement.
Okay.
Does that kind of make sense? Like, to be completely honest, I am unaware of which one the book takes as the definition of the word singular, because in my mind they're both the definition of singular.
And that's that goes back to the book denoting those matrices as C rather than A. Or is that something different? Because I know they labeled a certain type of matrix as C.
Oh, it's probably just that they were using letters up.
Oh, I just remember because they specifically said that one can't be invertible, or it's not invertible.
Okay. I don't believe that's a standard reference for the letter C. It probably was just the one spot they were talking about. But if you want to take a second later and find that reference for me, hit me with it in the Discord and let me know.
It is. I have it. It's 1.3. It's cyclic differences. It's page 25.
Perfect.
I may be remembering it wrong though.
Okay, so for reference, can you guys see this textbook?
Mm-hmm.
Okay. Yes. So this is not the only use of the letter C. They're saying that matrices of this form, which we're calling C right now.
Okay.
Yep. And yes, in this case, they certainly fail to be. They fail to be invertible. Is that cool?
Mm-hmm.
Okay.
Yeah, I'm good.
All right. Other questions on 2.1, number 7. Okay. In that case, I'm going to do